Okay, last week we went through the development of the digestive system up to the liver. We left the gallbladder and the pancreas to finish with the foregut. We'll do that today, and then we will go for the midgut and the hindgut derivatives. Now, the primitive bile duct gives rise to the gallbladder and the cystic duct. At this stage, and given the importance of the hematopoietic function of the liver in the growing embryo, this organ, the liver, represents up to 10% of the total body weight. You know that this function will later be transferred to the bones, to the bone marrow, and the liver will take its adult duties and will become smaller in relation to the total body weight. For now, let's say that as soon as week 12, the liver begins to produce bile. You know that bile is produced with bilirubin, which is because of the destruction of the red cells, and the embryo already has red cells, so it has bilirubin and it has to produce bile. Although bile is for the digestion of the fat, and the embryo is not doing let's say a digestion yet, because it doesn't eat. But most of the organs they have to start developing their function, so they are mature enough when the baby is born. Now with the pancreas it's the same thing. About the development, there are actually two pancreatic buds, ventral bud and a dorsal bud, which develop from the foregut endoderm, and the two eventually unite to give rise to a single organ when the duodenum rotates 90 degrees. If you remember, the stomach did rotate 90 degrees, and it drags the duodenum, and because the pancreas develops from the duodenum, from the endoderm of the duodenum, then it rotates with it. So going back to the pancreas, the exocrine pancreas generates when the endodermal tubules branch and form acinar cells and ducts, and the endocrine pancreas arises from isolated clumps of endodermal cells that will become the islets of Langerhans, the ones that produce insulin and glucagon. The splanchnic mesoderm that surrounds them will give rise to the connective tissue that supports the gland. And in this case, the pancreas begins secreting insulin around week number 10, which is very early too. As you can see in this sequence of images, the ventral bud in blue forms the uncinate process and a portion of the head of the pancreas, while the dorsal bud in red forms the rest of the head, body, and tail of the pancreas. Normally, the ducts corresponding to these two parts of the gland merge into only one, where the head's duct will correspond to the proximal third of the adult duct, okay? And the part that corresponds to the body and tail of the pancreas is going to represent 2/3, the two distal thirds of the adult duct. Now, just a few individuals may maintain the two independent ducts when they are adults, and this is important in relation to pathology. Basically, if they develop obstructions of these ducts. And that's it for the foregut. Now we go for the midgut. And the midgut gives rise to the third and fourth sections of the duodenum, also the jejunum and ileum, which are parts of the small intestine, and the cecum, appendix, ascending colon, and the two proximal thirds of the transverse colon, which are parts of the large intestine. So, the lower duodenum is the first part of the midgut and is connected to the foregut just where the Vater's ampulla is located. The Vater's ampulla is the opening for the common bile duct. The midgut, as we mentioned, it also gives rise to jejunum, ileum, the cecum, appendix, ascending colon, and the proximal 2/3 of the transverse colon. Now, if you take a more three-dimensional view of the midgut, we can see it lengthens a lot over a short period of time. And the abdominal cavity of the embryo at this stage is too small to hold all this growing in the body. So it forms, the intestine in this stage forms a loop that herniates through the primitive umbilical ring around week number 6. We'll see that in the next the two next slides. This herniation is called physiologic, meaning that is a natural herniation that will disappear when the abdominal cavity grows enough to provide room for all the abdominal viscera, and that happens around week number 11th. Well, in these images, you can see that the cranial limb of the primary intestinal loop gives rise to the jejunum and the upper part of the ileum, while the caudal limb forms the cecal diverticulum that divides into the cecum, the appendix, and also the distal ileum, the ascending colon, and the 2/3 of the transverse colon. Here the image in the top is showing how the intestines are forming that physiological herniation through towards the umbilical cord. So we can say that this primary intestinal loop protrudes inside the umbilical cord like a bobby pin, with a superior mesenteric artery growing between the two limbs of the loop. It's not represented here, but they are in between. The cranial limb of the primary intestinal loop initially develops above the superior mesenteric artery, and the caudal limb of the primary intestinal loop develops below the superior mesenteric artery. First, the loop will rotate 90 degrees counterclockwise around the axis of the superior mesenteric artery and moves the cranial limb to the right side of the artery and the inferior limb to the left, like a key that turns in a clock, but counterclockwise. So the cranial limb becomes very convoluted and will give rise to the future jejunum and ileum, whereas the caudal limb develops a small dilation that eventually develops into the cecum and the appendix. In week 10, when the abdominal cavity is big enough for the loop to go back inside the body, the loop rotates a final 180 degrees and moves into the abdominal cavity. Okay, so this happens between week 10 and 11. This rotation is such that the formerly caudal limb ends up framing the developing small intestine loops, which are above and to the right, giving rise to the ascending colon and the right 2/3 of the transverse colon. And that's it for the mid-gut. We have left the hindgut derivatives. These, remember, they are supplied by the inferior mesenteric artery. So the left 1/3 of the transverse colon, the descending colon, the sigmoid colon, and the upper part of the anal canal derive from the hindgut, which begins after the caudal limb of the midgut and extends to the cloacal membrane. The left 1/3 of the transverse colon, the descending colon, sigmoid colon, upper part of the anal canal derive from the hindgut, which begins after that caudal limb. The lower portion of the anal canal derives from the primitive anus, also known as proctodeum, which is a pit of ectoderm that forms just below the cloacal membrane. Also during week 4, the urorectal septum forms, and this septum is going to separate the cloaca into an anterior urogenital sinus and a posterior anal canal, which are covered by the urogenital membrane and the anal membrane respectively. So the upper canal develops from the hindgut, while the lower anal canal develops from the proctodeum, which is an invagination of ectoderm. At the end of week 7, the separation is complete and the anal membrane ruptures, so that the anal canal is now continuous and opens in the tail region of the embryo. The junction between the upper and lower canal is marked by the pectinate line, which is the spot where the anal membrane was inserted before disappearing. And this is all. Well, I think there is a reminder about the mesenteries. Then we will see a quick video on all these processes about the digestive system development. First, this is just to remind you that the gut tube is attached to the abdominal walls via ventral and a dorsal mesentery. Remember, the dorsal mesentery is much bigger than the ventral one. And now we can go with the video. This is a sagittal plane of the embryo. So you see the connection of the midgut with the yolk sac in yellow, and this is an transverse cut of the embryo. So the yolk sac is in yellow, and the endoderm layer is in yellow as well. So now the sides of the embryo grow and they meet in the midline, So the digestive, the gut, remains in the center. So here in this image you can see the respiratory diverticulum. Now it's gonna go below and see how the stomach grows and is twisted. So you see the nerves, the vagus nerves, they are to the sides of the stomach, but then when the stomach rotates, they stay in the front face of the stomach and the back of the stomach. And this is a 3D view of the stomach that is forming, and you have the dorsal and ventral mesenteries, and now you'll see how the stomach rotates 90 degrees, and that affects to the mesenteries that are attached to it. Also you see how the duodenum after the stomach is being twisted. Okay, and now it's gonna turn clockwise 90 degrees, and you see how the head of the pancreas is joining the body and the tail. This cut is to show better how it rotates clockwise 90 loop of the intestine with the two limbs, the upper limb and the lower limb. And now it's gonna rotate counterclockwise, a total of 270 degrees. And it's turning around the mesenteric, superior mesenteric artery. Now the sacrum is going to descend. you have here the final position. This is gonna grow bigger, but it already has the final position. Okay, here it's gonna show you the mesenteries that are holding, attaching the intestines to the body walls. Here what is very important is the urogenital septum. Here you have the arrow that represents that septum that will grow and divide the cloaca into an anal canal and an urogenital sinus. In blue you have the ectoderm, and you see how part of it goes into the joints to the anal canal. So it's an invagination. The final part of the anal canal is an invagination of the ectoderm. And that's it for this part.
That's all, folks.